Hello everyone. Last week in our lecture we discussed what we refer to as antiderivatives. So I just want to remind you of the antiderivatives. We said that a function f, capital letter F, is an antiderivative of a function small letter f if the derivative of capital letter F is equal to f of x. For example, if you take, for instance, capital letter F of x equal to minus 1 over 2 cosine of 2x, then we are saying that this is an antiderivative of small letter f of x equal to sine 2x, because when we differentiate this function using chain rule, we get sine x. So this is small letter f of x, this is capital letter f of x, like that, which gives us that one. Therefore, we conclude that minus 1 over 2 cosine of 2x is the antiderivative of sine of 2x. So similarly, one can take, for argument's sake, a function like f of x equal to maybe x cubed, and we can also have maybe g of x equal to x cubed plus say 4, and then we note that these functions are all anti-derivatives of our function. They are antiderivatives of our function small letter f of x equal to 3x squared. Why? Because if you take f prime of x, you get 3x squared. You take g prime of x, you get 3x squared, like that. And then you may notice that here it's just x cubed. This side would have got x cubed plus 4. But now they are all antiderivatives of the same one function, which is 3x squared. So in other words, we are saying that antiderivatives are not unique. Because you can have g of x equal to x cubed plus 3, and similarly x cubed, like that. You can even have h of x, say, equal to x cubed maybe plus 100. Is still an antiderivative of small letter f of x. So usually we can collect all the antiderivatives, and when we collect all the antiderivatives, it gives us this definition. Say the collection of all antiderivatives of a function small letter f is called the indefinite integral. Is called the indefinite integral of f with respect to a variable, say x in this case, and we denote this by use this symbol, which will give us the antiderivative of x. then plus c. Then if we compare what we have here with what we have up there, this c is like our 4 and also our 100. In this case, you can say plus 0. 0 is also a constant. So all these functions are the indefinite integral of f of x. In other words, f of x plus c, where c can be any constant, all of them are antiderivatives of this function. So moving forward, we recall some basic integration rules which are closely related to what we discussed in the first semester. Maybe just to remind you, you will recall that if you differentiate, say, a constant c, what do you get? You got 0, where this c is a constant. Now, let us reverse the process. When we reverse the process, we are saying that it means that the integral, the antiderivative, what did we differentiate in order to get 0 as an answer? We differentiated a constant. And then we have d dx of x, the exponent of n equal to nxn minus 1. To reverse this, we say the integral of x to the power of n dx equal to x to the power of n plus 1 over n plus 1 plus c. We are saying, what did we differentiate in order to get x to the power of n as an answer? And then we have differentiated the function. Then if you look at what we have here, since we said that all these are antiderivatives of a function f of x like that, then it tells us that the integral of 3x squared dx is going to be equal to 3x 2 plus 1 over 2 plus 1 plus c, which is, as you can see, we will have x cubed plus c, which is what we started off with there, because we said capital letter f of x equal to x cubed, like that. So this is how we get the antiderivatives, these functions. So c can be a 4, can be 100, it can be a 0, it can be any constant like that. Then you will recall that the derivative of sine x is cosine of x, as we've already noted. Then we can ask ourselves, if we have the integral of cosine of x dx, the question is, what did we differentiate in order to get cosine of x as an answer? And we know that we differentiate sine x plus c to get this as an answer. And then the derivative of cosine of x is minus the sine of x. So the question is, if we have sine x dx here, what did we differentiate in order to get sine x as an answer? We differentiated minus the cosine of x plus c to get this one as an answer. And we can move on to d dx. Say, for argument's sake, we spoke of the tangent of x. Derivative of tangent of x is sec squared x. Then it means the integral of sec squared x dx. What did we differentiate in order to get sec squared x as an answer? We differentiated tangent of x, which is tangent of x plus c. Then the derivative of sec x, we will recall, is sec x tan x. Then again, the question is, if we speak of the integral of sec x tan x dx, question is, what did we differentiate in order to get that one as an answer? We differentiated sec x. So we differentiated sec x. Let me clean this board so that you don't get confused. So this one is going to give us sec x, plus c. Then we can move on to the derivative dx of cosec x. Then you will recall that the derivative of cosec x is minus cosec x cot x. So if we speak of the integral of cosec x cotangent of x dx, we are saying, what did we differentiate in order to get this as an answer? We differentiated minus cosec x plus a constant c. And then the derivative of cot x is minus cosec squared x. So it tells us that the integral of cosec of cot of cosec squared x dx. What did we differentiate in order to get this as an answer? We differentiated cotangent of x, so it will be minus cot x plus c. Then the other ones that are important to us, here you will recall that the dx of e to the exponent of x is simply e to the exponent of x. So the integral of e to the exponent of x dx is e to the exponent of x plus c. And lastly, let me remind you that the derivative of ln of x is 1 over x. So this is telling us that the integral of 1 over x dx is equal to ln of x plus c. And then you observe that this is the special case where n is equal to -1. N is equal to -1 here, so we write it this way. And then dx of arc sine of x dx, this one we said it's going to be 1 over the square root of 1 plus minus x squared, like that, which implies that the integral now of 1 over the square root of 1 minus x squared dx is just the arc sine of x plus c. The other one is d dx of arctan of x So for that, the derivative of arctan, you recall it's 1 over 1 plus x squared, which implies that if you are asked to find the integral of 1 over 1 plus x squared dx, then you know that this is arctan of x plus c. So let us look at several examples. We are not going to repeat the examples we did last week, and we just put more examples. Then it is important for you to go over the rules of differentiation, and you know how to differentiate the various functions. Because if you don't do that, then it won't be easy for you to see what we are doing. Okay? So we may start off by looking at, say, the integral examples. Let us start off by looking at integrals like this, the integral of x, the n, the x, which is x n plus 1 over n plus 1 plus c. This is found on page 4 of our learning guide. You can check all the examples there. Of course, if we look at the integral of cube root of x dx like this, it simply means that we are talking of the integral of x raised to the exponent of 1 over 3 dx, which according to that formula is x 1 over 3 plus 1 over 1 over 3 plus 1 plus c. And this is like x to the exponent of 4 over 3 over 4 over 3, which is 3 over 4 plus c. So you just add number 2. Same, using that formula, let us take the integral of 2x squared plus 1 over x squared, like that, dx. This is equal to the integral of 2x squared over x squared plus 1 over x squared dx, which is the integral of 2 plus x minus 2 dx. This is the integral of 2 dx plus the integral of x minus 2 dx, which is going to give us 2x, because this is like x, the exponent of 0. So in other words, if I'm right, like 1 is the same as x, the exponent of 0, then we add 1 there. We divide by 0 plus 1. Then plus x minus 2 plus 1 over minus 2 plus 1. Plus, this one will yield its own constant. Let me write it, C1. This is another constant, C2. But a constant together with another constant is just a constant. So we've got 2x minus 1 over x plus c, which is standing for C1 plus C2, like that. And then we can move on to look at trigonometric functions. Say we spoke of the integral of sine x dx, which we are asking ourselves, what did we differentiate in order to get that? We differentiated minus the cosine of x plus c. The integral of cos x dx. What did we differentiate in order to get cosine of x? As an answer, we differentiate cosine of x plus c. And then the integral of, say, sec squared x dx, which will give us tangent of x plus c, the integral of sec x tan x dx, which gives us sec x plus c, and so on and so on. So let us take another example here. The other one which is of interest is this one, number 3, the integral of 1 over 1 minus sin x dx, like that. So when it is like this, we cannot apply any of these formulas. What we do, we must modify it in such a way that it will conform to one of those. So we have the integral of 1 over 1 minus sin x. Then let us multiply by 1. Multiply by 1 plus sin x over 1 plus sin x dx. Like that. This is going to give us 1 plus sin x over 1 minus sin squared x dx. And when we are there, still, we cannot use those. But we know that 1 minus sin squared x is equal to cosine squared x dx, which is going to give us the integral of 1 over cosine squared of x plus sin x over cosine squared of x, like that, all this dx. This is the integral of 1 over the cosine of x is sec squared x dx, plus this one is the integral now of sin x over cos x times 1 over cos x dx, which is going to give us, let me copy this, sec squared x dx, which is this one, plus this one is the integral sine over cosine is tangent x sec x dx. So let me increase the space that you can see. So we are saying this is equal to the integral of sec squared x dx plus the integral of tangent of x secant of x dx. And then sec squared x is there, tangent multiplied by secant, the integral thereof is there. So we end up with tangent of x for this one plus secant of x plus 1, just 1c, like that, which answers a lot of questions. I know one of you asked me last week about this integral, because you guys, you studied in a strange way. It was in the test, and then of course the person doesn't even know what to do here. So we okay. Let us take another example just to illustrate what we are talking about. So you can see the exercises on page 5, page 4 to page 5. I believe most of you have already done all of them. That's where you should start. Don't start with the first test and exam question papers before you even know what it means to find integration and how to simplify algebraic expressions. For example, if maybe you are given the integral of cosine of 2 theta over cosine of theta minus sine of theta d theta, like that. And then when it is like that, it's nothing much that we can do. But if you go back to page 3 of your notes, you will see that there is an identity which we can use. So this one, the numerator, they can be written as the cosine squared of theta minus the sine squared of theta over cosine of theta minus sine of theta d theta, like that. And this is equal to the integral. We can factorize this. This is cosine of theta minus sine of theta into cosine of theta plus sine of theta over cosine of theta minus sine of theta d theta, like that. Then we can cancel out this expression with that one. And we end up with the integral of cosine of theta plus sine of theta, put brackets there, d theta, which is going to give us now the integral of cosine of theta, d theta, plus the integral of sine of theta, d theta. And then from what we have just seen there, here, we end up with what did we differentiate in order to get cosine of x of theta as an answer. We differentiated, sorry, I made a mistake here. This is the psi of x. Sorry for that. So what did we differentiate in order to get this as an answer? We differentiated sine of theta plus c. What did we differentiate in order to get this as an answer? We differentiated minus the cosine of theta plus c, like that. So all of them repeat. We can take the last one there, number 5, the integral of x over the square root of x squared minus x to the exponent of 4 dx, like this. Then when we have something like this, you can see that this is the integral of x over, if we do it slowly, we can take x squared out, then we're left with 1 minus x squared dx, like that. This is the integral now of x over x square root of 1 minus x squared dx, which is giving us the integral of 1 over square root of 1 minus x squared dx. And what is this? This one we have seen is it's just arcsine, arcsine of x plus c. Why are we saying that? We are saying that because the derivative of arcsine of x is 1 over 1 minus x squared with the square root, like that. And finally, the integral, say, of du over 1 minus 1 plus u squared. This is just factor of u plus c.